The scintillation proximity assay, or SPA, is a type of radioligand binding assay used in drug discovery. It's used to measure the interaction between a drug and its target protein. It measures the affinity or tightness of drug binding. The technique uses microbeads that are directly attached to the drug target protein to assess binding. The beads are made of plastic and are only a few microns in diameter. The beads also contain scintillant, which is a substance that emits light when excited by radiation. Scintillant converts the energy from radioactive decay into a detectable light signal. To investigate the binding of a ligand to the drug target, the ligand is mixed in a solution with the microbeads. So that the interaction between the ligand and its target can be detected, the ligand is labelled with a radioisotope, making it a radio-labelled ligand or radioligand. The isotope could be tritium, carbon-14, sulfur-35 or iodine-125. The ligand therefore emits beta particles, which can stimulate the scintillant to emit a light signal that can be recorded. This cartoon illustrates what happens when the SPA beads containing the target protein are mixed with the radioligand in solution. The beta particles emitted from the radioligand in the bulk of the solution are dissipated without activating the scintillant in the bead, because they are too far away. However, when a radioligand binds to the target, it is effectively captured on the surface of the bead and briefly immobilized. It is now in close proximity to the scintillant molecules within the bead, so the beta particles excite the scintillant to emit light. In this way, light from the scintillant measures binding of the radioligand to the target protein. The light signal is monitored with a photodetector placed next to the beads. As light hits the detector, it sends out an electrical signal that is proportional to the amount of radioligand bound to the target. The signal is recorded and then analysed. Binding is studied over a range of radioligand concentrations. At each concentration, the light emitted by binding to the target protein is recorded. The first step in analysis is to create a graph by plotting the light intensity against the radioligand concentration. It usually looks like this. As the radioligand concentration increases, there is a steep increase in light emitted, indicating an increase in binding to the target. The relationship then gradually reaches a plateau level, above which increasing the radioligand concentration further does not stimulate more light emission. This indicates that all the available binding sites are occupied by the radioligand. In other words, binding is saturated. This type of plot is therefore known as a saturation plot. A property that we can measure from this plot is the dissociation constant, or Kd, for binding of the radioligand to its target. The dissociation constant is defined as the ligand concentration at which 50% of the target is bound. Drawing a horizontal line to the y-axis at the plateau level gives the light intensity at which binding is maximum. Draw another horizontal line from the y-axis at 50% of the maximum light intensity, which indicates 50% of maximum binding. Where it meets the saturation curve, drop a vertical line down to the x-axis. The value at which it crosses the x-axis is the dissociation constant. Scintillation proximity assays are relatively quick and cheap to perform, so they are widely used in high-throughput screening to identify potential new drugs. The assay is helpful for characterizing the pharmacology of receptors. In addition to measuring affinity, the kinetics of binding can be investigated by incubating radioligands with receptor-linked microbeads for varying times and measuring how rapidly an equilibrium is reached. Enzymes can be studied in a similar way to investigate interactions with substrates, products, and potential inhibitors. Scintillation proximity assays can also be applied to immunoassay to detect and quantify specific antibodies and antigens. They are also used to study signal transduction by measuring how signalling molecules or modulators interact with their targets. The assay can also be adapted to investigate protein-protein interactions, with one protein immobilized on the bead and the other labelled with a radioisotope.